Here's a concept that you might not be familiar with. It's the concept of the vacuum tube. I grew up in the vacuum tube era, just as it was evolving into the transistor era, and I had to learn how these things worked. That was back in the 1960s. In order to get my amateur radio license, I had to learn all about vacuum tube circuits and radio frequency oscillators and amplifiers that took advantage of vacuum tubes. But to a lot of you, I imagine that vacuum tubes are kind of an alien concept. They may seem kind of archaic to some of you, but then on the other hand, others of you may have had experience with vacuum tube amplifiers in large, high-fidelity amplifiers. Particularly, certain popular music bands prefer vacuum tube audio amplifiers to solid-state amplifiers. So let's just get a little handle on how a vacuum tube actually works and what actually is going on. This left-hand diagram here is a basic diagram of what a vacuum tube looks like if you could see through its metallic components. There's a glass enclosure called the envelope that's sort of usually shaped like a torpedo. Some of the old vacuum tubes have a shape resembling a large incandescent bulb. But you take this glass enclosure and you pump as much of the air out of it as you can to get essentially a vacuum. That's why they call them vacuum tubes. They also call them electron tubes, and that's because they work by transfer of electrons to produce the current inside them. This filament here is like the filament in a light bulb. You apply an alternating current voltage, usually about 12 volts AC, to this filament and make it glow red hot, and some tubes almost white hot. Well, I have seen tubes where the filaments glow white hot, anywhere from red to orange to yellow to white hot. So this filament gets extremely hot. It emits light, but its primary purpose is to heat up this cylindrical electrode that immediately surrounds it, and that's called the cathode, and that's analogous to the cathode in a semiconductor diode. You apply a negative voltage to this cathode, and then a larger cylindrical electrode around that, called the plate or the anode, collects the electrons. That usually has a positive charge. So electrons flow from the cathode to the plate, and this filament, its purpose is to heat up that cathode and drive those electrons off of it, or help to push them off, so that when the cathode here, this smaller cylinder, shown here in the schematic symbol, this is a diode tube, meaning it has two elements, the cathode and the anode, also called the plate. I don't know where the term plate really came from, because it isn't really shaped like a plate. It's shaped like a cylinder in just about all the vacuum tubes I've ever seen. Anyway, electrons can flow easily from the cathode to the plate because they're pushed and driven off of this cathode by the heat of the filament. However, if we reverse the polarity and put a negative voltage on the plate and a positive voltage on the cathode, then these electrons are going to have a mighty hard time getting back onto the cathode, because this filament is going to keep trying to drive them off. And the result of this particular state of affairs is a rectifier. You get easy flow of electrons from cathode to plate, like this, but much more difficult to get electrons to flow the other way. So electrons generally do not want to flow from the plate to the cathode. That is much more difficult. So you get, in effect, a rectifier, and you evacuate this enclosure, this envelope, in order to have the electrons easily flow between the plate and the cathode, or vice versa, I should say, easily flow from the cathode to the plate. You want that medium in there to be a vacuum so electrons can freely flow. Well, that's the basic and simple way that a vacuum tube can work. If you supply a negative voltage to the cathode and a relatively positive voltage to the plate, you might ground the cathode and then have a large positive voltage up here, something typically on the order of plus 400 volts DC. When you apply a large positive voltage like that to the plate of a vacuum tube, you get a good current through that tube. Now it varies depending on the type of tube. Small tubes might run with as little as 40 or 50 volts. Large tubes found in high power amplifiers, thousands of volts. But that's basically what we've got here, and that's how that situation works. But what I'd like to do now is take a closer look at this diode tube here. The cathode relatively negative, electrons flowing to the plate, and you get a steady current. And suppose you supply this plate with, let's just say, plus 400 volts DC. That's a good solid plate voltage for a vacuum tube. Alright, so we've got a current flowing there. Now we introduce an intermediate electrode in here. Something between the cathode and the plate. Now in the actual tube geometry, this is a cylindrical mesh, like a screen. It's called the grid. What can we do with this? Well, if we supply a negative voltage to this grid that's a fraction of this positive plate voltage, let's just say minus 100 volts DC, we will reduce the current through this tube. The more negative we make this grid voltage, the more we will reduce this current. If we don't put any voltage at all on the grid, we'll get the maximum possible amount of current. If we put a positive voltage on this grid, we normally don't want to do that. We will get a current that flows and leaks off through the grid. We generally don't want to do that with a vacuum tube. What we usually want is a negative voltage here, so that we can reduce the current that flows between the cathode and the plate. And by manipulating this voltage, we can adjust this current. If we make this voltage large enough negatively, we'll cut off the tube completely. No current can flow at all from the cathode to the plate, and we call that condition cutoff, just like we would call it in a bipolar transistor. But if you look at this principle, it really resembles a field effect transistor a lot more than a bipolar transistor. And in fact, you can think of a vacuum tube as working very much like a junction field effect transistor, or JFET. Works very much like that in principle, but with much, much higher voltage and power levels, and I might add, much better tolerance for transients and other anomalies that you sometimes get in power sources and signal sources. These tubes are far more robust, able to endure abuse a lot better electrical abuse, not mechanical abuse. Mechanical abuse, you drop one of these things from very high up, it'll explode or implode, I guess is a better word to use. Okay, so we get this negative voltage. Now, what can we do with that? I mean, what's the purpose of that? Well, it works just like a junction field effect transistor works. A small fluctuating negative voltage, or rather I should say small fluctuations in this negative voltage will produce significant variations in the current. And in that way, we can get a tube to amplify. Using feedback, we can make it oscillate, and we can basically work it the same way we would do with a junction field effect transistor, but just with a lot more power. So this tube, by the way, is called a triode. 3 elements. And it is the most basic form of amplifier and oscillator vacuum tube, a triode. It has a cathode, a grid, and a plate. The filament is not included in that count. And in fact, in schematic symbols, oftentimes you won't even see this filament included in the symbol for the vacuum tube. So that's a little overview of the basics of vacuum tubes, invented way back about 100 years ago. They still work. I've still got, I don't think any of my electronic equipment here has them. I don't think there's a single vacuum tube. Well, maybe there is in my television set, but I don't think so. Just the cathode ray display tube in the TV set. Otherwise, all my ham radios, all my computers, everything I've got now, it's all solid state. But tubes are still there, waiting to serve us in our time of need.